So our paper is about the neural networks, but consider the physical constraint to solve engineering problems. Um, uh, so this co-author, the first author is one of my PhD student, Day How do you? So, we have heard in previous talks, very, very nice summary how the engineering challenges we have been facing. So curse of dimensionality, actually, as a matter of fact, is the one of the major challenges for all of us. Because the so many design factors, parameter variables we need to consider as designers, engineers. Even machine learning itself actually has an issue like this, so-called curse of dimensionality. Just because of machine learning, most of the time we use machine learning to build a surrogate model, as we heard earlier in the talks. So the curse of dimensionality itself is just a visually, we can just look at on this figure illustration. If you have a large number of data points in a one-dimensional space, you can cover this region very nicely, very densely. So your surrogate model is pretty good representation. But if you increase the dimensions, go to two-dimensional, it becomes sparser, a lot sparser. If you go to three-dimensional, it's getting worse. So we, as engineer or designer, look into the many design factor variables to play with. So that caused the issue, so we just don't have enough data to build a very reliable surrogate model or input-output relationship, simply speaking. So in that case, statistically, we call the overfitting process, which means you have a surrogate model want to predict, but the prediction will be very, very bad, so which is not good. As an engineer and a designer, if we use machine learning to solve engineering problems, if you go to detailed design especially, we just don't have a luxury like the computer science people have a large data sets for us to work with. So that's the reason we say, is it possible for us to look into how to reduce the this bottleneck of at least alleviate the bottleneck of the lack of data or data sparsity for machine learning application in engineering problems, detailed design especially. So physics-based model becomes a very important aspect because physics-based, what is physics-based model? Basically, they're based on scientific knowledge. And then how do we come up with the scientific knowledge in the past? Hundreds of years accumulation, they are from the data as well. So this, basically, the data have been collected by those old engineers, scientists, mathematicians. They have done experiment. They have collected a lot of data already. So they build a knowledge, and we use knowledge. So we don't have to go back to the very beginning to collect data, do this learning again. So this machine learning models actually help us in the modern time, just because the processing power is so high, so that we can process a large amount of data. So we can do the data driven approach to to solve different problems. Now, of course, it had those two aspects, machine learning, data-driven approach versus physics-based approach. They have some good aspect as the limitation. In the physics-based modeling, you can have a good scientific knowledge. You have to learn the scientific knowledge, and but it doesn't mean your scientific knowledge is perfect. So that's some pros and cons using physics-based modeling. On the other hand, if you do the data-driven approach, you have good machines, computers to learn this fast, very, very fast, so that you can extract this correlation in a very fast way than the human being can ever imagine. But on this side, so you probably have to rely on the black box approach, because we consider the machine learning to become the tool, especially for engineers. It has limitation of the data itself could be the bottleneck. So how do you apply those, consider those two aspects all together, which was the starting point, and say, well, can we use this so-called the physics knowledge allow us to build a better in the sense of the more efficient in training. So you don't have to use a lot of data set to do the training, to solve engineering problems. So that was the starting point. And as a matter of fact, this is the physics-based approach for machine learning, especially neural networks. Actually, is not new, and this idea has been floating around in the past 30 years. And so there are different approaches people have thought of or developed, which is very good, genius ideas, I would say. So the first category of this approach is how to incorporate the physical meaning in architecture. So you design some neural networks so that you can incorporate this knowledge to have better structures. So one example, of course, is to say, how do we use neural network, that data-driven approach, say, as a pre-processing power, using this pre-processing tool to map some existing data. For instance, you have X, which is your some kind of parameter space or design space, map into the where the model required, which is the Z space. So finish the mapping for you. So it's pre-processing tool, which is one idea, of course. Another idea is say, well, if you have some model, the model is not perfect, and can we use the neural network, this type of data-driven approach to learn what are those discrepancy, which is the errors or uncertainty associated with the physical model. So we can use the neural network as in parallel and do the correction. So it's called a residual modeling approach. A third approach, is we use the neural networks and to just do the finish the mapping process is the input-output mapping process. And our physical knowledge could be used as some processing tools to pre-process this data so that to make it make more sense. So that is connecting physical model with the neural network, those ideas. So a second category of the how do you introduce physical knowledge into neural networks or machine learning tool is combine those information for neural networks as well as a physical model, such as this finite elements neural network idea here. We want to solve the problem, engineer a problem, say I want to predict the heat distribution, for instance. And then we can use FEA, traditional physics model. We can use some trained neural networks and to solve the problem. And as simple as look at this input-output mapping process. And this neat idea of this approach by Ramahali in 2005 is we want to embed this physical meaning into this neural networks weights. This is the most important thing, most important parameters we want to fine tune in neural networks. And what the authors did was just introduce this concept. We want to use instead of pure traditional we have trained the weights in neural networks. Rather, we say we want to embed the stiffness matrix, which is important in the FEA, which is fundamental, and to treat as weights as the stiffness matrix. Then you map to it as the domain, and then you don't have to train same as the traditional neural networks anymore. So this is the idea of combine this physical knowledge, put the physical meaning into neural networks. A third approach, which is also very interesting, is since neural network training process by nature is optimization, you want to minimize cyclical loss. And then how to consider those constraints and put a constraint into there, allow us to train this faster. So the constraint will be the guidance. This approach has been developed in the past more than 15 years, 2007. And so say I want to solve this problem in the PD, for instance, and then I want to use the training data to train. At the same time, the physical knowledge will be embedded as constraints in the training process, which is optimization. Constraint optimization, and to us, it's very natural to look at constraint optimization. You can introduce a regularization, for instance, and so on. So we took this third approach. So how can we use this called constraint approach to train neural networks? We formulate this problem, the training problem, as a constraint optimization and solve the high dimensional problem. That's the key here. How to solve a high dimensional problem as well as multi-physics problem. So in the past, people haven't reached that stage. How do you consider this multi-physics in the high dimensional design problem? It's good. What we're proposing in this paper is so-called multi-fidelity physics constraint neural network, or PCNN here. Multi-fidelity, as you learned in the previous talk, is you consider low fidelity information, high fidelity information, combine information together. You can have reach the prediction in a more efficient way during the training process. In our case, we can look into the low fidelity, just say a very simple, cheaper simulation. You can predict what happened with a long complete time period. We want to predict very short period, but using high fidelity and combine the information together. And then we use each neural network be trained and predict this low fidelity, long time, and high fidelity, short time. At the same time, how to find the difference or discrepancy here? We have to train this, a third neural network to find the discrepancy, which is the delta here. And then we can add those information back to predict the whole long time period for this discrepancy here. Um, so the prediction, by the way, of course, is just you have a low fidelity to predict a long whole time period between 0 to t, and add this discrepancy term and to predict a whole time span. That was the goal here. In terms of detailed formulation, how this so-called constraint optimization can be applied in the training process. The process pretty much can be looked at. We want to say solve the time-dependent PDE as one say example. F here and highlighted red is the target physical property quantity we want to predict. We can use simulation, for instance, to predict a traditional one, and then you can find out the training process pretty much just to find the difference between the neural network prediction versus the true value, true solution. So this is traditional in the neural network training process. Now, we want to add constraints to make the training more efficient. So the constraint OPF, so the ET here in the so-called total loss function has been extended. Original training data is the ET, which is the loss function based on the training data itself. Now, adding constraints, so such as the physical model, how physical model physical constraints are satisfied, which is EP here, the blue one, as well as, say, initial condition, how those initial conditions are satisfied, which is EI, as well as the, say, boundary condition, E of S. And then our total so-called loss function has been extended in the physical constraint scenario. Just add all those 4 constraints together with a weighted average. So that will be our total loss function. So the training process, of course, to solve this minimization problem. And one of the key, I would say, the important bottleneck in the training physics-based physical constraint neural network is how do I assign this the lambda here? This lambda, the weights, they're very important. If we assign it in an improper way, the training process will be very inefficient. So we came up with a new idea. So how do we adaptively train, and by changing this weight scheme, which is the lambda becomes a so-called adaptive scheme. In this new total loss function E here, we use the ratio between the current stage of the training loss versus the total loss altogether, so that we can adaptively. So if one, say, for instance, physical constraints loss is higher, then the weight should be higher, so that we try to reduce that portion of loss more quickly. So that's the idea here. Some example here, we just quickly show how we have been achieving the so-called training more efficiently. If you look at that figure for the heat transfer problem, and our goal is try to make sure all the 4 losses are going through the reduce proportionally. So that is good. Our adaptive training scheme works. On the right-hand side, the chart shows how the training compared to traditional neural network without physical constraints, how efficient it is. So it shows with the same number of the data points, we do the training, and then the physics-based physical constraint neural network can reduce the error faster, smaller. So that is good news. And so this is just an example to see how the prediction of the temperature field will be different. With say on the top is the original FEA simulation. On the bottom left is the neural network, traditional neural network. With of course, we intentionally have a small amount of training data. At the right-hand side, we use the PCN, which make the prediction much more accurate. So here's another example, the phase field, which is the multi-physics problem with the heat transfer and the grain growth, so-called phase change, phase formation process. So you can see on the left is the temperature is a prediction of the FEA, and top is phase field, bottom is temperature field. In the middle is we use one setting with a PCNN, which is the multi-fidelity. We choose different. We have to choose different training data sets as well as the topology of neural networks carefully. So that's the bottleneck for us, is how do you find a good topology or architecture of PCN, which is very important for us to do in the future work. Okay, in summary, what we have seen is the physics knowledge actually improved the training efficiency as we observed. And so that's the multi-fidelity is a good balance between efficiency and accuracy, as in the previous talk we also heard was learned. Now, how to look into physics-based physics constraint neural network? We have to go way back to a lot of questions we have talked about in the design is about the black box versus the white box, or gray box. So there's a gray box, which is physics constraint neural network. How well it can perform. So those options we need to find a good balance for different problems, and then how to use the PCNA for the future design. And so obviously, PCN doesn't replace existing or say we already know the simulation model. We cannot replace that, but we can use it as a reduced order model to make it efficient prediction. And so, is it possible? How can we do that? So those things will be all the question ahead of us. Finally, the training of the PCN actually has the major issue, same as the traditional neural network, how to train this fast, easy. So how to formulate. So that's the idea. We recently published paper, you see, we formulate in different ways. Instead of training the neural network as the minimization, we train it as a set point search, which is solving this min-max problem itself. Yeah, thank you very much.
Okay.